Hello, preview. All right, guys. Hello. I finished grading the homework. I will send it back today. I'll also send you your next homework assignment. Grades were pretty good. There's some of you guys need to look at your calculus, taking derivatives in particular of things that are not explicit. There was some bad in that, but other than that, most of the grades were pretty good. When we left last time, we were dealing with the E over M experiment that Thompson did, and we had talked about the fact that if we were starting it, we were only going to look at the electric field, and we were not going to apply the B field yet for the beam filtering, so that's where I'll pick up. And I had gotten to the point where we were talking about the angle of deflection, which he could measure because he has a screen out here, so he can measure how far along this curved screen that he deflects the beam with the electric field. But what he can't measure is the velocity component in the y direction, so he's trying to get rid of that. So when I left, we talked about the fact that the plate was very small compared to the length of the tube, and so he was able to just treat it as traveling in a straight line with no force after it left the plates, and that's determined by that angle, which is determined by the velocity component in y and the velocity component in x. And so he takes and writes the tangent is the y component of the velocity over the x component of the velocity, and then he rearranges it. Like that. And in particular, what he's interested in is he knows the angle is going to be small. And if the angle is small, then the tan of theta is approximately theta. So he can measure the angle, and he knows the tangent of the angle. If he could find Bx, then he has found By. And so he substitutes this in to the expression we had before, and now he's got Q over M is the speed in the x direction squared. So he's still got that problem. How does he find the speed of the particles? Because he can't use a stopwatch and count them. The distance between the plates, which he can measure with a ruler, the voltage on the power supply, which he knows, and the length of the plates, which he can measure with a ruler, and this angle, which he can measure on the screen. So send it through with no deflection plate, make a mark, put the deflection plate on, turn it to a voltage, measure the angle that the beam gets deflected. So if you can measure this, then you can get this Q over M. This is where the B field comes in. Thompson was a smart guy. So he knew the basic physics that existed in his day. You don't get to be the director of the Cavendish Laboratory at Cambridge without knowing some physics. All right? So he knew about beam filters, or cross-field analyzers, also known as velocity filters that we had in physics too, and that's what he plans to use. So what he does is he does this, he deflects the beam, and then he comes on and he puts his magnetic field on. So when he turns his magnetic field on, he has an electric force, like that, but he also now has a magnetic force, down. And if he adjusts the magnetic field just right, he can make those two forces cancel, and the beam go back undeflected straight to the point where it started. So if we do that, the sum of the forces in y, here's my x and y, my free body diagram, if that's 0, then that says that the electric force minus the magnetic force is 0. And I remind you from physics 2 that the electric field is QE, and the magnetic field, which is the Lorentz force, is Q speed, which is Vx, times V. And because they're at right angles, the cross product, the sine of theta, is 1. So this field depends on charge. That force depends on charge. The charge is going to cancel out. This one depends on the electric field. This depends on the magnetic field and the speed, and I want to use that to find that speed. So since that is equal to 0, I can combine this to say QVXB is QE. And I can cancel the Q's. And then Vx is simply the electric field over the magnetic field. Now when you do this, it's called a velocity select. Now the guy who did it was Bean. No, not Wien, Bean. So it's also known as a Bean filter. Because the fields are perpendicular to each other, it's sometimes also called in the literature a cross-field analyzer. These are not too bad, and accelerator systems have them. In fact, one has it on my machine for our ion accelerator, provided the voltage is not voltage, but the energy of the beam is not too high. Yeah.
How does he make a constant V field like that without like a huge solenoid?
Well, what you do is you build two coils, and you run current through the two coils, and in the region between the coils, the magnetic field is basically perpendicular. You can do the same thing with a, for instance, a rare earth magnet by cutting the poles to shape the field. Now, that means you have a small size, but he didn't need a very big size. He just needed small. So Helmholtz coils were known. In fact, earth-canceling coils are common in lots of things. If you actually go into an atomic physics lab, you'll see people have coils like this big or even bigger, and on top, and they'll have a coil on the bottom, and they will cancel the magnetic field of the Earth. Because the magnetic field of the Earth is sufficient, if you're doing like electron studies, to deflect the electron so that it doesn't get through your collimators to your detector. So, I mean, they spend hours matching around, making sure there's no magnetic field anywhere. I'm not patient enough to do that type of experiment. I smack things. All right, you get a big ion, you don't have to worry about it. You just run over everything. It makes it a lot easier. But people who do astrophysics or electron experiments, they use these chemicals all the time. So this was fairly easy, well-known stuff. What you need, of course, is a steady current, so you need a good power supply. But that's easy to do. Electrical engineers are real good about building constant current power supplies. No problem there. Now, build the beam filter. Not too hard of a problem. Of course, he didn't want to work with the electric field. Let's put it back in terms of our voltage. So the one thing I would probably want to change here is I want to remind us that we've already got this relationship that the electric field times the distance in the plates is equal to the voltage difference across it. So we can replace the electric field by the voltage that we're using on the power supply, because that's what we can measure off the dial. And so that's what he had. So now what he does is he takes this and he plugs it in for Vx squared. And you see that you get a voltage squared on the top, you have a voltage on the bottom, so one of them cancels. You got a magnetic field which gets squared, it goes on the bottom. You have a d squared, which cancels one of the d's on top, so you get a d on the bottom. You have a length of the plate on the bottom. And then he says, hey, look, because these are going to be small angles, if I measure them in radian, the tan of theta is approximately theta, something we're going to use a bunch today. I put it right there. So if I do that, then that becomes theta. And he decides to go one step further, and he says, look, what I'm going to do is I'm going to rewrite the equation in terms of theta. So I'm going to put theta on one side, which he does. And I'm going to put everything else on the other side. So the b squared comes up, the d comes up, the l comes up, and the v. And he says, I'm going to call that x. And I'm going to call that y. And if I plot that, given that b's constant, d's constant, l, and b, if I set those values and I leave them alone, and then I plot theta on the y-axis, what does this equation graph? What will that equation graph?
Will you move the paper up a little bit?
Oh, I'm sorry. I'm off. If I make this v squared dl over v, if I plot that along x, and if I plot theta over here, So I set a value of BDLB, get a number, and then I measure the angle, and I plot it.
It's a line.
Straight line. So I said do some plots. I should get a straight line, and the slope of that line should be
Screw Q.
E over M. That's how you found the E over M for the electron. So if you look in Roth's book, he's got some actual data that was published in the original publication in 1897. You know, it doesn't look as nice of a straight line as what you draw because it's data. So he's got data plotted for different values here and plotted against different angles, and here's his data around here. And it's been done with a lot better precision since, and you basically come to a straight line. And you get E over M from the line. Straight lines are useful things in interpreting data because the human eye can see linear equations better than others. But you often have to figure out what you're going to plot over here to make something look like a straight line. So, it deflects. Electric and magnetic field. So it is a charged particle. It's not a photon. Not only that, they tried all sorts of different metals for things at the end. These cathodes, they always got the same slope. So that means that all of them put the same particles out. And that particle was the electron. And that they knew what the charge per mass ratio was. Now once you've got an E over M, when they eventually then went ahead and found E in milligans, then you now have the mass of the electron. You have fundamental properties of it. So that's what Thomson did. Now, your problem. You want to build a model of the atom. And the model of the atom has to obey and give all the facts that you know at the time. And here's facts you know at the time. You know that the atom is neutral. You know that electrons are in it and they're negatively charged. So that means there need to be some electrons in your model. But it also means it's got to be neutral. So that means it's got to be something else too. You know that electrons can be emitted. You can knock them off. We just did. And you also know that they can be knocked off in chemistry experiments because you know about electrolysis in the 1800s. So you need a model that's got a neutral atom, explains electrolysis, explains why you knock electrons off, has the right size, preferably, or at least a rough estimate of that size. But you also need to explain why positive charge isn't seen coming off. And you'd also like some other things, like spectral lines. Well, Thomson tried as best he can, and we'll come back to some problems with Thomson's model. But he tried all sorts of ingenious things. So, basic ideas to just put in your notes. Electrons exist in atoms. You know that now. And they're negatively charged because of the way they deflected. We could tell the charge. If they'd been positively charged, they would have deflected the other way. An atom is neutral. So it must have an equal amount of positive charge. The fact that the electrons come off means the electron has to be kind of concentrated, someplace you can punch it. The fact you don't see the positive charge might mean that it's distributed somehow, spread out, so that you can't get as good a momentum transfer to it. Thinking about that, Thomson came up with the following model. He says there's going to be a bunch of this positive charge, but it's going to be spread out, not concentrated. And it's what gives an atom its size. And to explain the fact that I can knock electrons off, I'm going to concentrate the electrons. I'll make them discrete. He called this a plum pudding model, and he thought of raisins. I don't like plum pudding, so it's a chocolate chip model. All right, so I got my chocolate chips. There's my little chocolate chips are my electrons, and my cookie, which is my positively charged spread out. We know the negative and positive charges attract. But why are they sitting on top? Why not in the center? This is a problem in the Thomson model. In fact, you can figure out what that's going to be, and I'm going to come back to that in a minute when we do Gauss's law, because it's going to indicate that there should be a continuous spectra that's being produced out of here, and it should also indicate that the electrons all go to the center, collapsing basically to a singularity. Thomson, to solve this problem, attempted all sorts of geometry arrangement. Maybe the electrons could be arranged such that they repel, but the positive charges attract. And he tried to put them in quadrilaterals, triangles, tetrahedrons, and so forth. He basically went back to the idea that Kepler, about this idea of regular solids, where Kepler had tried to fit the planets, and the fact that he knew at the time that there were 5 and only 5 planets he could see. It all fails. But at least it's a model that explains some things. And that's often all you can do with a model, is explain the best you can and work from there onward. So that's what he did. Now, Thomson had a student by the name of Rutherford, Ernest Rutherford. Rutherford took these electrons and started putting foils in front of them as a student. And he was, to test this model, shooting electrons through the foil. If the positive charge is diffuse, you're most likely not to get much of a force. You fly through it, and you don't get much of a deflection. And I'll prove that in a second. And that's what he saw. So there was some evidence of this. Rutherford left, went off on his own, found alpha particles, christened them the alpha particle. It makes sense that if he had a new particle to shoot, he should shoot them back at these poles again. So he does with his students Geiger and Marsden. And it's that where we find the nucleus, because we begin to see deviations from what this model expects. Before we do that, I want to deal with Gauss's law, because I'm going to need it for the type of proof I'm going to do. So I'm going to skip a page in my notes and deal with Gauss's law, because I want to come back and talk a little bit about Gauss's law and how it applies to the Thomson law. So I remind you in Gauss's law in E and M, which you should know, that the integral around a closed surface of E dot dA, where dA is a differential element of the area on the surface, and E is the electric field, is called the flux, or more precisely the electric flux. And if you integrate over a closed surface, for a closed surface only, which is why the circle, then it's equal to the enclosed charge inside of that area divided by epsilon naught, the permittivity of free space. To find the enclosed charge depends on the problem. But what it is, basically, is the integral around a volume of the charge density with respect to that volume. All of that should be old hat, and you should be able to pull that off your head. But I want to go back and look at it a little bit, because now that you're sophomores, you should be known through Cal 2 to Cal 3 and be doing DEF-E by now for your junior courses. So let's take a look at one of these surfaces. That surface at a distance r. To apply Gauss's law and actually be able to do something, although it's true, we don't do Gauss's law to do Gauss's law. We do Gauss's law to find E. And to find E, it's got to be able to be pulled out of that integral. I cannot pull it out of that integral unless I can find a surface on which it's constant. So that's one condition. And that means I have to know something about the field lines. In the case of a spherical shaped charge, those field lines look like this. So unless I have a symmetry of some sort, although Gauss's law is true, it's not very useful for anything. So that's one thing. I want to choose a surface where every point along the surface, the electric field's magnitude is constant. Now, let me go one more step to show why I want to do that. E dot dA, that's E cosine of theta dA. So I want to be able to pull that magnitude out of that integral, and I can't do that unless around that surface that I'm integrating on, which means little places like this, it has to be the same value of each one of those little rectangles. And that's a three-dimensional sphere. That is not a circle. Okay? So I could write it for a rectangle. But if I write it for a rectangle, I couldn't pull the E out. Another thing I need is on each one of those, there's a differential area dA. So let me draw to the side. There's some little dA like that. And there's some E. There's a cosine of an angle between those two. And if that's not a constant or not easy to determine, I can't pull that thing out either. I've chosen a surface where the electric field lines go out and the dAs are parallel to them. And since there are two vectors that are parallel, what's the angle between those? Got two like this, what's the angle?
Zero.
Zero. What's cosine of zero? 1. You can apply Gauss's law where that's not true, but it's not of a lot of use. What that lets me do is pull that E out, that 1 out, and I just have the integral dA, which is the area of the sphere. Point being is I need to choose a surface which makes that integral easy to evaluate. On the other side says over volume, and it's the volume enclosed by that surface area. And that's an interesting thing. These are two totally different things. This one, I'm going to be adding up all this stuff in here. We talked about that some in physics too. Isn't it amazing that something added up along the surface tells you what's going on the inside without actually ever being at that point in space? Yes and no. It's like the outside of a balloon. The area of the balloon, its skin, determines the volume inside it. You have a similar thing with if you go and you deal with Stokes' law. You've got this line integral around the outside like on a drum head, but how you tighten the outside of the drum head determines the area that it binds. So if you change the tension of the drum head along the line, you change what happens in the middle of the drum where you hit it with a stick. Go back and look at Calculus 3. Make sure that you understand conclusively what those things tell you. And as you take those to your junior level courses, we'll expect you to know them. Okay? In this case, not all the charge is inside. There was a charge, whatever this Q is, but some of it's in here and some of it's outside. And it says you only count the enclosed charge. Now, in the particular problem, Thompson and others are going to assume a uniformly charged sphere. What does that tell you about rho? Charge density.
It's constant.
It's constant. What do you do with constant? Pull it out. So we can pull this rho out with the integral dV, which is the volume, but only the volume that's been hatched inside of here, not the total volume of the atom. With that, let's finish the problem like we did back in physics 2. I pull the E outside. I have the integral dA. I pull the rho over epsilon naught. I have the integral dV. Oh, sorry, just dV. This says that the electric field times the area of my sphere is equal to rho over epsilon naught times the volume of my sphere. So the electric field is rho over epsilon naught V sphere over A sphere. Now, without going into a lot of detail, you should already know something about it. What's the units of a volume?
Meters cubed.
Meters cubed. What's the units of a sphere?
Meters squared.
Meters squared. So this thing is going to have the units of meters. This thing is going to grow linearly as you change that sphere. This is true for all things that are uniformly charged inside, whether they're a plane or a cylinder sphere. Hey, remember our Darth Vader? We had the death sphere and the death cylinder and the death slab, and I was going to kill Luke Skywalker. Aiden built the death sphere, and it fell us, had this linear, and then it fell us 1 over r squared. But he figured that out, and then he went to the death cylinder, went 1 over r, and then I killed him with the death slab and psychologically tortured him. All right? That's a universal thing about inside. You get this linear relation. By the way, if you multiply this by q, then the force is also linear. That means it's like a harmonic oscillator. So if you had an electron attached inside the sphere going back and forth, it would have a restoring force like a harmonic oscillator. It would oscillate. It would have a force. That means it would accelerate. But if it accelerates, it would do what? It would radiate. And if it radiates, it would lose energy and eventually would stop. If you pull a spring back and you let it go, when it eventually stops, where does it stop? At what value of x? 0. So all the electrons would end up in the center. So if that's the model, all the electrons in Thomson's model should have been in the center, and they should have radiated anytime they were disturbed in continuous spectra, not spectral lines, both of which are not observed. Let me go ahead and put some numbers, or some formulas in here. I got E naught, the volume of the sphere is 4/3 pi r cubed, where r is the radius of the small sphere. On the bottom I have 4 pi r squared. Notice the 4 pi's cancel. And the electric field turns out to be rho over epsilon naught. I have a 3, and I have an r. And to make it a vector, just put an r hat. Now, if the total sphere was an atom, say of helium or something, that had a total charge of Z2e, I can also replace this rho. So let's assume that Q was some atomic number times Z. Then rho would be Q over V total, which is Z2e. And on the bottom, V total would be 4/3 pi big R cubed. And I could put that in here. All right, so if I do that, I'm going to get on the top Z2e. On the bottom, I'm going to get 4 pi epsilon naught r cubed times r hat. And I want to do one more thing with it just to simplify it a little bit. But 1 over 4 pi e naught is k, 9 times 10 to the 9th Newton meters squared per Coulomb squared. So I get Z2 EK r cubed times r hat. So it goes linearly with a constant. By the way, if you make this equal to r, to save yourself a lot of time, if you make this thing r, then you're going to get kq over r squared, which I know off my head, and so I would never spend all this time deriving this for myself. I would have gone straight to that in one line. That's called experience. Hopefully, you should, by the time you're junior year, have that experience. Certainly by the time you get to E&M class. So the electric field goes up something like this. Now, Gauss's law outside of the sphere. You can do all of the Gauss's law stuff over again, but you should know what happens when you're outside a sphere. What does it look like?
Coulomb's on.
Yeah, it looks, well, Coulomb's is the force, but it looks like a point charge. Just like when you're outside the planet Earth and you look back, it looks like a point mass. So we know the electric field for a point charge. So it's K and the Q, which is Z2E, over R squared. Just like that. So where's the largest electric field located at?
The boundary of the atom.
At the boundary of the atom. Okay, that would be the largest electric field you could have. When R is equal to R. Anytime else, you would either be further away and experience less, or you'd be inside the positive charge, you'd experience less. So if I just assume that I had that big of an electric field, I would overestimate the force that this point would apply to anybody that came at it. Because when I'm further out, it would be a less of an electric field and therefore less of a force. And if I was inside, it'd be a less of an electric field. So I'm going to overestimate. Why do that? I avoid differential equations and I avoid a lot of calculus. And I get a very simple answer that explains why Rutherford decided to form the nucleus in his model. And I don't have to do nearly as many pages. Now, if you want the full-blown differential equation approach, there are plenty of nice books that will be glad to give it to you. And certainly for senior level students, I would expect to be able to do this, and I do in nuclear classes. But basically following classical mechanics of potentials and working your way down step by step, conserving energy, conserving angular momentum of the central force, and so forth. I'm going to bypass all of that.
What book is that?
I'm going to overestimate the deflection. And what I'm going to show is that the deflection I get is going to be very small, and it's an overestimate. I'm going to estimate that you don't even deflect this thing a few degrees. And instead, we're going to get deflections. I deflect routinely in my lab 180 degrees deflections. So that means there's something wrong with the Thomson model. I'll show you how I can get that. And I'll avoid all this calculus. But I have to know that electric field, and I have to know Gauss's law to be able to do it. That's all from the freshman physics class. Okay. All right, so let's look at what Geiger-Marsden did. Geiger-Marsden had this thing in kind of a radioactive source. It was difficult to get radioactive sources in those days. You basically had to ask Madame Curie. The source emits radiation in all directions, so you don't want that. So what you do here is you build some sort of a box around it, and you put a hole. So then it basically becomes a gun. You evacuate the area, and you put some sort of a foil, and then around that foil, you put a fluorescent screen that shines when it gets hit. Now, they don't shine real bright. These are not advanced detectors like today. So you put yourself a little eyepiece here with a little telescope.
So they're not scintillating crystals then?
Huh?
They're not scintillating crystals then?
No, they did not have scintillating crystals, nor did they have the Geiger counter. You'll understand why Geiger invented it. All right. So he's sitting here looking for a flash. And he wants to measure over a given time how many flashes at each angle, moving small increments at a time. Now, it was easier to build a sphere because you blow into glass. So this thing turned out to be all the way around on this foil. And not only that, but on top of that, when you put the fluorescent material in, it goes everywhere. So they had to backcode it, although they didn't plan to use it. They expected them all to come out here. But one fine day, they had the telescope in the wrong place. And they just decided to look. And lo and behold, they saw some of them bouncing back. This is like shooting a Volkswagen at a piece of tissue paper and having it bounce off and come back at you. That is pretty remarkable. So most don't do it. Most go straight through as expected, but some do get deflected, and that doesn't seem to be logical. So let's see if we can prove how that works. Well, let's see. The force would be Q times E on the alpha particle. So if you did the electric field times the charge of the alpha particle, you can get that. I know what the charge is on an alpha particle. Rutherford had measured it already with this E over M. It's Z2E times the electric field. Now what we're going to do is we're going to assume the largest electric field we can. Thereby, I don't have to consider how the electric field changes as it goes through space. So I'm just going to make it an overestimate, and I'm going to overestimate that force. So if I do that, I get Z2E, and then I would get, I'm sorry, my fault, this should be Z1. I want to call the particle coming in 1. Number 1 is incoming. I need to be consistent here. Number 2 is target. You don't have to choose whichever one you want, but I got to be consistent. So this one happens to be Z1 would be 2 for an alpha particle. And Z2 would depend on your target, and they tried different targets. They tried nickel, they tried gold first, they did silver, they did copper, almost any type of metal they could make it into a thin film. So Z1E, K, Z2E, over the radius of the atom squared, times R hat. Assuming that I did all my things right. Now, there's some things you might want to do with this. First of all, it turns out you're going to run into a lot of problems where you have K and E. It's convenient if you put these two electric charges on the electron together with that K and rewrite it kind of like this. Ke squared is equal to 1.44 eV nanometers. A useful thing to note. Know this. Notice again, we see this energy times space, just like we had with HC. It shows up throughout physics. There's a connection between them. Also, you can change this. You can make this KeV, and then this becomes a picometer again. You can make this MeV, this becomes a Fermi. So if you have energy levels of MeV, you're dealing with spaces of Fermis. This happens to be the size of the nucleus. These guys actually create and determine the size of atoms and nuclei from fundamental constants of the universe. You have no control over these. The reason that an atom has the size it does is it has energy levels on the order of electron volts. And this is why batteries are in volts. They're not going to be in megavolts. They deal with chemistry. The size and the energy are connected, fundamentally. Can't exchange it. We will find for this particular problem more useful is 1.44 MeV Fermis usually. So given that, let's look at it. Well, I got a force. Great. What I want to find is I want to find a change in momentum, which can roughly, if I assume the force is constant, because I'm going to overestimate again, times the delta t. Now, how long does this particle last? Well, the maximum force is somewhere like, right here. And then out here, it's less. Let's just do this. Let's say all the time, in here, it's a maximum force. Let's overestimate again. So I'm not going to integrate and find the actual distances. I'm just going to say, oh, what the heck. Let's just say that it moves this speed, and it does it for that distance and use kinematics and overestimate. Well, if I do that, 2r is Vx delta t. I can find delta t then. That would be 2r over Vx. Again, it's not that long. We're overestimating. I'm now going to take that delta t, and I'm going to take this force, and I'm going to overestimate the deflection, the change in momentum, by plugging it in here. Okay, E squared, Z1, Z2, R squared, and then I want to multiply that by 2R over Vx. See, that's going to kill one of those, kill that. And I'll just tighten it up a little bit. 2k E squared C1 Z2 over Vx bar. Now I still got a problem because, Vx isn't the thing I normally want to measure. I have a rough estimate on the size of an atom. I know what the atomic numbers here are, and I know what that is. So if I knew this, I could find delta P. I'm not going to find delta P, turns out. I see a Vx here. What I know in collisions is important is what's conserved in collisions?
Momentum.
Momentum. So I'd like P. So tell you what, I'm going to work in terms of P. So I'm going to multiply the bottom by an m to get P. That's my initial momentum. And I'm going to multiply the top by m. So here's an m. On the bottom I got mvx. Well, that's just my initial P. 2m over P, okay, E squared, Z1, Z2 over R. Now, let's go back to our little electron deflection problem. I tried to figure out a deflection by treating it after it collided. It left the thing and went as a straight line. Same thing here. It's going to see an atom. I'm not going to consider multiple scattering or such. It's going to hit that, go through the film, fly across the apparatus and strike my screen. So that atom is on the order of angstroms. The distance to my screen is on the order of, centimeters, meters long. So after it sees this force, it's basically a free particle, travels in a straight line. I'm going to treat it as such. So there's P, there's delta P, and it's going to travel like this in a straight line until it hits the screen. Well, I can do another tan angle thing. That would be delta P over P. Hey, I got a formula right up here for delta P. So I put that in here. 2m, okay, E squared, Z1, Z2 over R. I had one P, I get another P, that's over P squared. Now, what's P squared over 2m equal to? Classical physics.
Kinetic energy?
Kinetic energy, 1F mv squared. So, fortunately, it was classical. It predates, a real good thing, relativity come along, but it wasn't like people were using it. Fortunately, it is classical, and that's the energy of the beam that I sent in, which I can measure. So, but E squared over 2m is the E. By that I mean the energy, not the electric field, of my alpha. It's a free particle flying through there. It's all kinetic. So I now have this is K E squared Z1 Z2, the electric field, and the size of an atom. What I think an atom is, which I know somewhat from Avogadro's work in chemistry. So let's put some things in there. If the radius of an atom is about an angstrom, which we know it is from Avogadro and chemistry, if we take a 6 MeV alpha, they're mostly about 5.35, 5.7. They're none above 8, and they're not below about 4. So take 6. I put in the known atomic numbers. 2 for the alpha, 79 for gold. Gold's mass is 197. Its atomic number is 79. You should know that. There's the energy. Put those in. Here's what I come up for an angle. The tangent is 3.79 10 to the minus 4. That's small. So therefore, that's the angle in radians. And that's an overestimate. Now, you may object to the fact that I'm assuming only one collision. And that's a good point. The foil is made of many atoms, and so maybe it'll go through many collisions. But here's the thing. Sometimes it might come through and get deflected up, but it also might get deflected down with equal type of probability. So on average, there's equal probability going up and equal probability going down. Where's the distribution's average value going to be?
Right in the middle.
Huh?
Right in the middle.
Right in the middle, 0. So what we're looking here is the standard deviation of a distribution function. And this is a many event of equal probability. This is a Gaussian distribution. Well, I can calculate standard deviation.
Remove those two.
It's whatever one event is times the square root of the number of times this thing is flipped. So all I need to know is roughly the square root of the number of atoms in the foil. Multiply by the value of 1, and I will get, within 60-something%, what the standard deviation, all of them will be in that angle. I'll do it 2 times that, 3 times that, 5 standard deviations. I don't care. 5 standard deviations, there's like no probability it's going to be outside of that. Well, to do this, there's space between the atoms. Let's overestimate. Let's assume there's not. Let's stick them one after another. So we get as many atoms as possible in the foil. We know the thickness of the foil. We know the distance across the foil. We can divide the thickness by the distance of one atom and find the number in the foil. It overestimates, but that's okay. We're overestimating everything. So roughly did that. And I said there's about 10,000 atoms that it can bounce off of. So I take the square root of 10,000, I get 100. I take 100 times that, and I still only get this. 5 times that. That's not even, you know what, 10, what's that? 5 times is like 0.1, let's see, more than that, 0.17 radians. Extremely small. So this thing is not going to scatter at pi over 2, much less at pi. All right? No way. So if that doesn't happen, what's the problem? So here's where Rutherford puts his thinking cap on. He says, okay, that's really small. There's no way this model says you can deflect that much. We need a bigger force. We need a bigger angle. All right, that's fixed. I can't change K in Coulomb's law, and I can't change the charge of an electron. The energy is measured to the alpha. It's not negotiable. The atomic number of helium is 2. You can't change it. The atomic number of the foil is unchangeable. The radius of the atom? Well, I assume the radius of the atom was where the positive charge was spread out. What can I do to R to make this number become bigger? Make it smaller. So if I was to shrink R smaller, then the angle would become bigger and I get bigger deflections. He just figured out how small he needed to make R. That's where you put the positive charge. And hence you come up with the nucleus. Now, once you do this, you can go back and do some calculations on probability about how does it depend on Z1, how does it depend on Z2, how does it depend on E. And he did that. That probability is called a scattering cross-section. And he came up with this formula. He said the probability depends on the square of the target. So what he did? He made Geiger and Marsden go back in there, put different targets, and measure around. Months and months and months and months at a time. He wanted to change the energy. He had no accelerator. He couldn't turn the energy down. So he made them cut small pieces of mica and put it in front of the target beam, measure its deflection with a beam filter, and then go back and repeat the experiment over again. Months and months and months and months at a time. Geiger and Marsden decided, man, this is going to be a real pain. They thought they might make some good detectors. Geiger invented electronic detection called a Geiger counter. Marsden decided to make the scintillators glow better. He invented a scintillation that didn't turn out to be useful for this, but made flash cubes for a company called Sylvania. And he got rich, making flash cubes for cameras. Right? But their purpose was to try to make it easier for themselves. After they did all this, they confirmed that formula. And that's how we know that the nucleus exists today. So, Rutherford's final model looks something like this. Got to be a positive concentrated charge. So if you come in like this, the force is not very great and it goes through. But if you hit right on, you get a much larger electric field and a much larger force and you get deflected back. You still have discrete electrons. Now there's some argument, and I haven't read his original paper, of whether he put these in orbit or not. It makes sense that he did, because otherwise he's got a force they're going to fall in. So that's what you would do. The problem is they're charged. And since they're charged, when they go in a circle, unlike planets, they should radiate and spiral inward. It explains alpha, but it's unstable because they should radiate. So the electron should slow down. The electron should
decelerate.
Must be accelerating. Thank you. No, this one, I got it backwards. This is accelerating. There we go. And this one is radiating. I get it right. All right. Trying to hurry and I'm getting myself in trouble. So it must lose kinetic energy. So it will slow down. And it will fall into the atom. So if I was doing this, this electron should do something like this. And as it does that, it's going to change. It'll initially emit like red light, and then it'll pick up some speed and it'll emit like green light, and eventually it'll emit other light. And you'll see a continuous band, and nobody saw that.